Assalamu alaikum warahmatullahi wabarakatuh. Good afternoon, everybody. Today we will start in chapter 9 power series. This is the last chapter in this subject. In this chapter we will learn 3 sections. What is the meaning of power series, how we can calculate the power series for the function, and Maclaurin theorem. So what is the power series? What is the power series? Power series is the power that have this form, which is a polynomial form. It is a polynomial, infinite polynomial form. The first term is a constant, where x to the power 0, The second term is constant times x, c1x, then plus c2 x squared when n equal 2, plus c3 x cubed when n equal 3, plus ckx to the power k. This is similar to the polynomial expressions, and this is the powerful of power series, or the advantages of power series, that it is a polynomial expression which is easy to calculate the derivative, easy to calculate the integration, and so on. So any series have this form, we called it a power series. Any series with this form, which is a polynomial, infinite polynomial form, we call it a power series. Here c0, c1, c2, c3 until ck are real numbers. X squared, x cubed are the variables. So when this series is converged, when we can say that this series is converged, when we can say that this series is diverge. Actually, for any power series we have interval of convergence. We have an interval of convergence. Outside this interval, it is a diverge series. So when we said that the power series is converged at a point alpha, which means it is converged on the interval around alpha. All this interval around alpha, the series is convergence. When I say that the series diverge at beta, which means this is the area of divergence. Area outside this interval, this is the interval of convergence for the series, and this one is the interval of divergence. So for each power series we have area for convergence and area for divergence. And for some power series, the area of convergence may be all the real numbers, so no area of divergence. But each power series should have at least one point of convergence. How we can determine the interval of convergence for the power series? To determine or to calculate the interval of convergence for a power series, we need to apply either a ratio test, maybe a ratio test or root test. We have to apply either a ratio test or a root test. If we apply the ratio test or root test, we can find the interval of the series, the interval of convergence of the series. Regarding the boundary for this interval, we have to test each boundary by a separate case. So we need to do 2 steps. First step, we have to apply a ratio test or root test to find the interval of convergence. Then we need to check the boundary of these intervals, if the series diverge on this point or converge. Let us go, for example, if we have this value, okay, for what value of x do the power series converge? Which, in other words, what is the interval of convergence for this power series? The interval of convergence for this power series. So the first step here, we have to apply the ratio test. Ratio test means that limit when n goes to infinity. Now instead each n, we replace each n by n plus 1. We replace each n by n plus 1. I will replace n, this n will be replaced by n plus 1, n plus 1. X to the power n plus 1 over n plus 1 divided by minus 1 to the power n minus 1 x to the power n over n, which is equal to the limit when n goes to infinity to minus n minus 1 minus 1 x to the power n times x over n plus 1 times here we will change the division here to multiplication. We'll change the division here to multiplication, and we flip, we make that top below and below top. So here this is times n over minus 1 and minus 1 x to the power n. So here minus 1 to the power n plus 1 minus 1 become minus 1 to the power n plus 1 times minus 1. X to the power n plus 1 is x to the power n times x over n plus 1. The division will be converted to multiplication, and we flip this one, so we have n over minus 1 to the power n minus 1 x to the power n. Now we will cancel, so you have to cancel this one with this one, and this one will be cancelled also this one. So you have only limit when n goes to infinity to limit when n goes to infinity minus 1 x n over n plus 1. So minus from absolute value will go outside. Minus will be cancelled with the absolute value. So this is will be equal to limit when n goes to infinity n over n plus 1 times x, the absolute value of x. Now here the limit of n over n plus 1, this one direct substitution give you infinity over infinity, so I will divide by the highest power. So this one limit when n goes to infinity 1 over 1 plus 1 over n times x. So this one when n goes to infinity 1 over n becomes 0 and 1 over 1 become 1. So you have 1 times absolute value of x. 1 times absolute value of x. No need to write 1. Here we can cancel 1. So this is absolute value of x. This is absolute value of x. Now based on the ratio test, we have to be the function to or the series to be continuous, the limit should be less than 1. The series to be convergence, the limit should be less than 1, then the series converge. If the limit greater than 1, then the series diverge. If limit equal to 1, the test fail, the ratio test fail. So here we need to find the interval of convergence of the power series. So we need to find where is the point of x where the absolute value of x is less than 1. Then in this case the limit will be less than 1, and then the ratio test converge, the series will converge. So we need to solve this inequality to know at what value of x the absolute value of x is less than 1. So this one, to solve the absolute value less than 1, which means x is between -1 and 1. X is between -1 and 1. So -1 and 1 is your interval of integers. Okay, from -1 and 1. But we need to check first at all these points, from -1 until 1, the series converge. But we need to check the boundary. We need to check 1 and -1. I have to check the boundary. So I will check x -1 first, and then x equal to 1. So at x equal to -1, okay, go for the series. Substitute x by -1, replace x by -1. So you will get the series like this. If you substitute x -1 as the series, you will get the series. And from 1 until infinity, -1 and -1 and -1, and x will be replaced by -1. So you have -1 to the power n over n. What I did, I go for the series here. For the series, I will replace x by -1, the first point I have -1. So this one will become the series or summation from n equal to 1 until infinity, -1 n -1 plus n is 2n -1 over n. If we check this series, this series at n equal to 0 is at n equal to 1 is equal to -1. At n equal to, it become -1 over 2. At n equal to 3, it become -1 over 3. At n equal 4, it become -1 over 4. So if you notice here, this series, it is always -1, -1. So it is the series of n equal to infinity, -1 over n. At n equal to 1, -1. At n equal to -1 over 2. At n equal to 3, -1 over 3. At n equal 4, -1 over 4, and so on. So this is your series when you substitute x by -1. This is minus is outside as a constant. And this one is diverge harmonic series. This means at this point, at x -1, the series is diverge, not converge. So it will not be included in our interval of convergence. By similar way, we need to check at x equal to 1, the second point of interval, because our interval is from -1 to 1. Now we check at x -1. We have also to check when x equal to 1. So at x equal 1, we have to go and substitute here again. Go for the original series, replace x by 1. So your new series will be summation from n equal 1 until infinity minus 1 over n minus 1 1 over n 1 over n. This is alternating series. Alternating series. So this is alternating series. So we need to check the alternating series test. So alternating series test, we need to check 1 over n. Is it decreasing or not? And is it limit equal to 0 or not? So here 1 over n minus plus 1 is for sure less than 1 over n, so it is decreasing. And we have limit of 1 over n goes to 0. So alternating series converge. So converge alternating series. By alternating test, it is a converge series. So x equal to 1 is included in our interval of convergence. X equal to 1 is included in our interval of convergence, this one. So our interval of convergence will be from minus 1. Then the interval of convergence is minus 1 not included, but 1 is included. 1 is included. So it is from minus 1 and 1. So first step, we have to apply the ratio test or Roos test to know the interval of convergence, and then we need to check the boundary as a separate case, to see if the boundary of these intervals are included in the intervals or not. In our example, minus 1 is not included, but at x equal to 1, the series is converge. So this is another example. We have this power series, and we need to know the interval of convergence. So first we have to apply ratio test. So to apply ratio test, we need to take limit when n goes to infinity for xn plus 1 over n plus 1 factorial, okay, divided by x to the power n over n factorial. So this one will be limit when n goes to infinity to x to the power n plus 1 is x to the power n times x. N plus 1 factorial is n plus 1 times n factorial. Here the division will be converted to multiplication, and we will flip the second fraction, so we become n factorial over x to the power n. Now you need to cancel x to the power n with x to the power n factorial with n factorial. So you have limit when n goes to infinity 1 over n plus 1 times the absolute value of x. So here when I substitute n by infinity, this one n by infinity, so 1 over infinity here is 0. 0 times x is 0. So this limit equal to 0 times absolute value of x, which is 0. What we mean that the limit equal to 0, this limit equal to 0, that means that the interval of convergence is equal to R, all the real number. The interval of convergence is all the real number, So here at all real number the series converge, at all the real number, and our radius of convergence is R. Here for this example, our radius of convergence is equal to 1 only. We have our series is centered at 0 because it is a Maclaurin series. All Maclaurin series are centered at 0. So here the radius of convergence is equal to 1. The radius of convergence in this example from 0 to 1 is equal to 1. But for this example, the radius of convergence is all the real number, because R is convergent on all real numbers. Okay, this is the third example. How we can calculate the interval of convergence for the power series. This is an alternating power series, -1 to the power n minus 1, x to the power 2n minus 1 over 2n minus 1. So first step, we have to calculate the ratio test. So limit when n goes to infinity -1. For the ratio test, we need to replace each n by n minus 1. Each n will replace by n plus 1. So n plus 1 minus 1. X 2 n plus 1 minus 2. Minus 1. So this one minus 1. Over 2, I will replace n by n plus 1 minus 1 divided by -1 n minus 1 x 2n minus 1 over 2n minus 1 over 2 minus 2n minus 1. So this is the ratio test. We replace each n by n plus 1. X to n, replace n by n plus 1. Here also we need to replace n by n plus 1 divided by -1 to the power n minus 1 x to n minus 1 over 2n minus 1. Now limit when n goes to infinity. Here -1 n minus 1 times -1. This one -1 n minus 1 times n minus 1. X 2n minus 1, because this one 2n plus 2 minus 1. So 2n minus 1 2 times n minus 1 plus 2, which means we have x squared. Over 2n plus 2 minus 1, which is plus 1. Here plus 2 times 1 plus 2 minus 1, which is plus 1. I will change division to multiplication and I will flip the second fraction. So 2n minus 1 over -1 to the power n minus 1 times x to n minus 1 times 2n minus 1. Now we need to cancel again, but before going to eliminate the terms, here minus 1 n plus 1 minus 1 is minus 1 n plus 1 times minus 1. X to n plus 1 minus 1 is x 2 times n is 2n minus 1 times x 2 times 1 is x squared, so 2n minus 1 x squared over 2n plus 2 minus 1 is plus 1. I changed the division to multiplication and I flipped 2n minus 1 become on the top, then minus 1 to the power n plus 1 x to the power 2n minus 1 become below. So this one will equal, now we can eliminate this term with this term, minus n with minus n. So we have limit when n goes to infinity to minus x squared 2n minus 1 over 2n plus 1. 2n plus 1. And this one, limit minus from the absolute value can be positive, so you have only 2n minus 1 over 2n plus 1 times x, absolute value of x squared when n goes to infinity. Now here when n goes to infinity, this will give you infinity over infinity, so we need to divide by the highest power. So here this will be equal to the limit when n goes to infinity. This one, direct substitution, give you infinity over infinity, divide by n, so you have 2 minus 1 over n, 2 plus 1 over n, absolute value x squared. So substitute n by infinity, this becomes 0, 1 over infinity here also 0, so 2 over 2 which is 1. Now 1 times x squared, absolute value of x squared, so it is equal to absolute value of x squared. This is equal to absolute value of x squared. Now this one, so this is equal to absolute value of x squared. So this is the ratio test. Ratio test to be convergence, the series to be convergence, the limit should be less than 1, because we need to find the interval of convergence. So we need this limit less than 1. This limit is less than 1. And this means that x squared, because this is positive, less than 1, so x itself should be from minus 1 and 1. When x squared less than 1, which means that x, or the absolute value, when you take the square root for the both sides, so absolute value of x will be less square root of 1, which is x from minus 1 and 1. So this is your interval from minus 1 and 1. This is the interval of convergence centered at 0, because it is a Maclaurin series. Your radius is equal to 1. Now we need to check the boundary point at 1 and x minus 1. We have to check at the boundary point. So at x equal to minus 1, at x equal to minus 1, we will go for the original series, this one. We will replace x by minus 1. So we have summation when n from 1 until infinity, minus 1 and minus 1, minus 1 and minus 1. Now x will be replaced also by minus 1. We will replace x by minus 1. Why? Because we test the series at x equal to minus 1. So 2n minus 1 over 2n minus 1. So we go for the original series. We replace x by minus 1 because we test the series at minus 1. So change x by minus 1. Change x by minus 1. So this series becomes summation from n equal infinity minus 1 here 2n minus 1. 2n minus 1 is 3n minus 2. 3n minus 2 over 2n minus 1. So if we check this series at n equal to 1, substitute n equal to 1 here. So become 3 times 1 is 3. 3 times 1 is 3. Minus 2 is 1. So minus 1 to the power 1 is minus 1. Over n equal to 1, 2 minus 1 is 1. So minus 1. Now when n equal 2, we have 3 times 2, 6, minus 2, 4. Minus 1 to the power 4 is plus 1. Over 2 times 2 is 4, minus 1 is 3. Now when n equal 2, when n equal 3, 3 times 3, 9. 9 minus 2 is 7. 7 is an odd, so this one is minus. 2 times 3, 6, minus 1, 5. Okay, when n equal 4, 3 times 4, 12, minus 2 is 10. 10 is an even, so minus 1 to the power n is 1. Over, when n equal 4, 2 times 4 is 8, minus 1 is 7. So minus and so on. So if you have a look here, we can notice that we have 1 minus 1 plus, 1 minus 1 plus, which is an alternating series. This one is alternating series. Minus 1 to the power n over, we have here 3, 5, 7, all are odd, which is 2n minus 1. 2n minus 1. So this is our series. It is alternating series. Alternating series. So we have to go for alternating test. This one is alternating series. So we have to go for alternating test. Alternating test, we need to check if this one is decreasing or not, and limit equal to 0 or not. If we check the decreasing, we can easily prove that 2n plus 1 minus 1 is less than 1, 2n minus 1. So this one decreasing. Now limit 1 over 2n minus 1, when n goes to infinity, is 0. So this one converge alternating series. So we will include the point x minus 1 in our interval. So this point will be included in our interval. Now we need to check at x equal to 1. I will check at x equal to 1. So at x equal to 1. Same. I have to go for the original series. Sorry. This one. This series. I will replace x by 1. Change x, put 1. So your new series is summation when n equal 1 until infinity minus 1 n to the power n minus 1 x by 1 to any power is equal to 1. So 1 over 2 and minus 1. When you replace x by 1 here, so 1 to the power 2 and minus 1 is 1. X to the power 2 and minus 1 will be 1 because x is replaced by 1. So 1 to any power is equal to 1. So we just write 1. So this is also alternating series. This is also alternating series. Applying the alternating test, we can find it is a decreasing because this one is correct. So decreasing, and also limit for this sequence equal to 0. When n goes to infinity, limit equal to 0. Limit is equal to 0. So also converge. Now also at x equal, so at x equal to 1, also we have a converge alternating series. So the second point or the second boundary point is also included in our interval of convergence. So the interval of convergence here is all the point, the interval of convergence here is from minus 1 and 1, including also the point minus 1 and the point 1. So this is the interval of convergence. Any point, the series is convergent at any point between minus 1 and 1, and also at minus 1 and 1. So this is all the interval of convergence. So generally, to find the interval of convergence of a power series, you have to apply the ratio test first. If you get the limit equal to 0, like second example, then the radius of convergence is the all real number. It's the all real number, like this one. Limit 0, so the interval of convergence is all the real numbers. So your interval of convergence is equal to R. Now, if the limit equal to absolute value of x or absolute value x squared, you have to get to make the limit less than 1, because the ratio test states that if the limit less than 1, if the limit of an plus 1 over an less than 1, the series converge. Greater than 1, the series diverge. Equal to 1, test fail. So here we need to know where the series is convergent. We need to make the limit less than 1. Solving the inequality, find the interval of x. For this example, from minus 1 and 1. This is your interval of convergence. So you need to check at the boundary now, at the point minus 1 and 1 separately, if they are included in our interval or not. If the series converge at this point, they will be included on the interval. If the series is not convergent at this point, they will not be included in the interval. So here we test first at x minus 1. How we do the test? We go for the original series, this one, replace x by minus 1 first, the first point, minus 1. So you have minus 1 to the power 2 and minus 1. Minus 1 to the power 2 and minus 1. So this is your series. This is your series. This is an alternating series. So you have to apply the alternating test. And then at x equal to 1, you have another alternating series. Also converge. This means that the both points have to be included in the interval. In our first example, we included only 1 point, because at minus 1 the series was diverge, not converge. When we replace x by minus 1, we get a diverge harmonic series. So minus 1 not included in our interval of convergence, only the point 1. only the point 1. Okay, this is another example for the power series, but this example the power series is not centered at 0. The center here is x equal to 1, x equal to 1. The center here is x equal to 1. Why? Because we have x minus 1. Here we have x minus 1. So the center is not 0 like a previous example. The center of this power series when x minus 1 equal to 0, which means that x equal to 1. Now we need to know the radius of convergence. The radius of convergence. So we have to apply the convergence series, the ratio test. So ratio test, we have square n plus 1. I will replace n by n plus 1. So we replace n by n plus 1. X minus 1 n plus 1 over divided by square root of n x minus 1 to the power n. So limit when n goes to infinity, square root n plus 1 x minus 1 to the power n x minus 1 times 1 over, I will change division to multiplication and I will flip the second fraction, square root of n x minus 1 to the power n. So limit when n goes to infinity, square root n plus 1 over n. Now x minus 1 to the power n will be cancelled or eliminated with x minus 1 to the power n. So we have only x minus 1. And this one equal to limit when n goes to infinity, square root n over n is 1 over 1 over n times the absolute value x minus 1. So now here when we direct substitution with n equal to infinity, so 1 over infinity is 0. 1 over infinity is 0, so square root of 1 is 1. Square root of 1 is 1. Sorry. And then you have limit equal to absolute value x minus 1. So limit will be equal to x minus 1. To be convergent, this one should be less than 1. To be convergent, this one should be less than. So to know the radius of convergence, we have to make the limit less than 1, the absolute value of the limit less than 1. So this one will be from minus 1 less than x minus 1 less than 1. So we need to know the radius of convergence. So between minus x minus 1, since the absolute value x minus 1 is less than 1, this means that minus 1 less than x minus 1 less than 1. Solving this inequality gives that x between 0 and 2 by adding 1 to each side. Plus 1 plus 1 plus 1. You get that it is x between 0 and 2. Here we have the absolute value of x minus 1 less than 1, which means that minus 1 is less than x minus 1 less than 1. Add 1 to each part, which means that x between 0 and 1. So your interval now is from 0 until 2, centered at 1, because the series from the beginning center, the series center, each power series has a center. If this center equal to 0, like the previous 3 example, we call it Maclaurin series. if the center not equal to 0, like this example, the center was equal to 1, we call it Taylor series. So we have, this is interval, radius of interval is 1 equal to 1, from 2 minus 1 is 1, but our interval from 0 to 2, so my interval is from 0 to centered at 1. So to check this interval, we have to check the boundary point, if the 0 and 2 are included in our interval or not. So we need to check at 0 first, at x equals 0, so your series at x equals 0, okay, we can go here. This is the original series. So at x equals 0, so square root of n minus 1 to the power n. Square root of n minus 1 to the power n. So we have square root of n when x equals 0, so we have minus 1 to the power n, when n from 1 until infinity. So this one is alternating series. Alternating series. Alternating series means we have to go for alternating test. If we go to alternating test, limit square root of n when n goes to infinity is equal to infinity, not 0. So diverge series, which means that 0 is not included in our interval. Now we have to check at x equal to. At x equal to, we will go for the original series again, and we replace x by 2. X will be changed by 2. So you will have this series summation at x equal to, we have summation from n until 1 until infinity, square root of n we replace x by 2. So we have 2 minus 1, which is 1 to the power n. 1 to the power n for sure is 1, so this is your series. We need to check this series is converge or diverge by going for divergent test, by using divergence test. We have limit. Divergent test, you need to take the limit for square root of n when n goes to infinity is equal to infinity, which means diverge series. So also x equal to not included in your interval of convergence. So the interval of convergence is only from 0 to 2 without the points 0 and 2. So the interval of convergence is 0 and 2. The open interval 0 and 2 without including the point 0 and the point 2. Only between 0, all the points. The series is converged only for the points between 0 and 2, but it is not converged at 0 and 2. And outside this interval also it is diverge. So by this example, we finished the part 1 for chapter 9. We still have a part 2 for chapter 9, which is Maclaurin series, and how we represent functions by using power series. So this is what we will learn in the next class, inshallah. Thank you.